G'day. I've had requests for an encore, so here we are, ready to go through a beautiful Mathematics B lesson, Queensland, Year 11. Our topics, we're going to do quadratic functions, we're going to do parabolas, which are in effect graphs of quadratic functions, and we're going to do a little bit of rationalise the denominator. You may notice the time. It is completely inappropriate. None of us should be awake at this hour. Don't expect perfection, and that's not because Sir had a big night. That's tonight. No, I'm looking forward to a good night's sleep. But here we go. Maths for today, one take, errors and all. First up, we're going to look at, quadratic functions. Now, most of this you would have seen in Year 10. So here we go. Quadratic functions, general form, y equals ax squared plus bx plus c. So compared to a linear equation, it adds this ax squared thing, which is all very exciting and makes it very different when it comes to the mathematics of it. Now, when you graph one of these things, you get a happy face or a sad face, which more technically, a happy face we call a minimum, as its turning point is at the bottom, and the sad face we call a maximum because its turning point is at the top. So if I just sketch a random minimum, it's not perfect. I hope you can forgive that at this hour. Let's talk about a couple of the characteristics of what I've just drawn on here. So I already mentioned the turning point. So that's technically the point where the gradient is 0. There is a point there where the rate of change, the gradient, if I draw a tangent line, a line that has the gradient at that point, you get a horizontal line. So there is a turning point there. It's a minimum turning point. And essentially, it's where the gradient is equal to 0 is your definition of that. You'll find that these things tend to cross the y-axis. How many times can they cross the y-axis? Thought about it? Good. Once. All of them should cross the y-axis once. So we call that, of course, the y-intercept. Then we have points where your parabola can cross the x-axis. What do we call them? That's right, x-intercepts. How many x-intercepts can a parabola have? 0, 1, or 2. This one obviously has 2. If I drew one up here, it could have 0. If I drew one that just touched on the x-axis, it could have 1. So they can have 0, 1, or 2 x-intercepts. What else did we want to show? X-intercepts can also be called zeros. Occasionally you'll also see them called roots. Anything else we need to include? Technically parabolas are symmetrical. If you take what's on this side, flip it over, you should get exactly the same thing. So you could draw a line down here at x equals a certain value, and that is the axis of symmetry. So it's symmetrical, it's the same either side from that line. So there's your base parabola concepts. Now we're going to return back to quadratics. Certain things we want to go through. So I'll give you a challenge first up. We're going to do a chook pen. Yes, we are going to build a chook pen. Now, in various examples we've done other things. I've done horse yards, cow paddocks. You know, whatever you really enjoy, I'm happy for you to do it. But essentially, you have enough fencing wire with enough fencing materials for an 80-metre chook pen. Find the maximum area. So there's a little quirk here, and that is that we're going to have an existing fence line. So this is an existing fence line, and here is our proposed pen. Now you've got 80 metres worth of material from which you can draw this. What's the biggest area you can get? What are the dimensions you're going to use? Now, if you're feeling really like a challenge, I'll just leave you to think about that for a while. Go for it. Okay, so here we are. With these sort of problems, I highly recommend first defining your variables. So, what we could do is we could go, well, let x be the width of the chalk pen, and we could let y be the length of the chalk pen. Right, so first of all, I've defined variables. Secondly, and this is, we'll do a lot of this style of question next year. There's a whole unit called optimisation in grade 12 Queensland Maths B that deals with optimising these sort of situations. And in that process, part of it is we express what we want to maximise in one variable. Now at the moment, there are two variables up there. We've got x and y. Now what did we want to maximise? The original question. What was it? Area. We want to maximise area. Now normally we'd say area is length times width, which in this case is x times y. But there's two variables. Always in these questions there will be enough information to turn it down to one variable. So let's do that quickly. We know that this side plus this side plus this side has to be 80 metres because that's your fencing material. So 80 metres of fencing material has to equal x plus y. So 2x plus y. Right? 2x plus y has to be 80. I can now find an expression for y. Take 2x away from both sides, I'll be left with y is equal to 80, take 2x. Isn't that magnificent? So this here, instead of y, I could write it as 80 take away 2x. Therefore, area being x times y, it's going to be x times this expression. X, 80 take away 2x. Now, at this point, I could just graph it, and for our purposes I am going to graph it, but I might just expand this first so you can see that it's a beautiful quadratic. Right? I'll draw the claw. I'll do a couple more claws later when we're talking a bit further on matters. That will give me 80x take 2x squared. I can put the x squared at the front. It'll be negative 2x squared plus 80x. Right? So in this case, we're going to graph and interpret. And this is one I prepared earlier. Here we go. On our friend Desmos, which again, we're not allowed to use for assignments, but we can do for a bit of fun in class. Now, if you graph that, you'll first find that it looks absolutely like rubbish. You'll notice my axis here. See how it's going up in 200s on the y-axis and it's only going up in 10s on the x-axis? If you ever need to do that, just click the little spanner there and you'll find you can manually change where the x-axis is going between and the y-axis, and that's how I've got it to look as good as it does now. So essentially at the moment, remember how we defined our variables? X is the width and y at the moment is the area. So the maximum area is up here and I can click on it in this software. So essentially it's saying that the maximum area is when x is 20, so the width is 20, and the area is 800. How cool is that? So back here, I'm just going to write that up at the end. So the maximum area, when width is 20 meters, which means the length has to be 80 take away 2 times x. That's 80 take away 2 times 20, so the length will be 40 meters. And that maximum area was 800 meters squared, which makes sense. 20 times 40 is 800. So that's a cool example of an application style harder question that you could get relating to quadratics, and that was going to be our big introduction question for this lesson. So I hope that that was all sorts of enlightening and fun, and be prepared to experiment with that. Maybe you could even do 100 meters of wire or something different if you want to see that process up close and personal and all that sort of stuff. But now I'm going to move on to the second part that I need to cover with you guys, and that's revision of quadratics, expanding. It's all about expanding binomials. So say goodbye to this beautiful work. It's all going to go. Here we go. All right. So here we go. A little bit about expanding binomials. So firstly, you may want to recall what a binomial is. So it's one of these things. X plus 3, x take 5, or something like that, right? It's got two main parts that are in brackets and we need to expand them. Now at this point, some of you may look at this and start talking about something called FOIL, which really embarrasses me, and I'm glad I'm not hearing you say it. I hate FOIL. It's no, I don't actually hate FOIL, it's more an apathy, The opposite of love is apathy, and apathy is definitely the appropriate response to FOIL. So, alas, look, I do something called the claw that I recommend because you can use it in a lot of situations beyond just having 2 bits in each. So, essentially, everything in the first brackets has to be multiplied by everything in the second. So, I draw a claw to make sure that I do that I multiply everything in the first brackets by everything in the second. And from there, hopefully you can't go wrong. So I have x times x, which is x squared. I have x times negative 5. Remember, negatives always belong to what follows it. X times negative 5, negative 5x, plus 3 times x, so plus 3x, plus 3 times negative 5, which is negative 15. Simplify that, x squared will be negative 2x, negative 5 plus 3, take 15. Right? You need to be extremely proficient and comfortable in doing that. So, why I like that claw thing? In fact, let's do a harder example. You're thinking, that's too easy, isn't it? Let's do something really hideous. Let's do something like x squared take 4x plus 3 times x to the power of 3 take 5x plus 1. There we go. Now this is going to be messy, but if we stay true to the principle that everything in these brackets has to be multiplied by everything in these brackets, it'll be all right. So the claw this time is going to be more intimidating. Now let's see if we can do this quickly in a video where I only do once without stuffing it up. So that will be x to the power of 5, take 5x to the power of 3, plus x squared, take 4x to the power of 4, plus 20x squared, take 4x, plus 3x3, take 15x, plus 3. Now just have a breather on that. Does that work for you guys? All of that times x squared. All of that times negative 4x. And all of it times 3. That looks all right. We've now got to combine the like terms. There's only one with the power of 5 on it. Looks like there's only one with the power of 4 on it. Then I've got that component and that component to the power of 3. Then I have that one and that one with the power of 2. 21x squared. Normal x's then, I've got those two, so subtract 19x with just the plus 3 on the end. Did you guys get the same? Is that all cool? So you have one there, I have one there, and all of them involve combining. No, that was the only one there, that's right. So one term in there, one term in there, one term in there, and there were 2 each in there. 9 terms. Okay, there were 9 terms in here, and I know that I took 9 terms into account there. So hopefully that's all good. So that's why I prefer dealing logically with the claw. I think everything in this times everything in this, and we're all happy. If I made an error there, tuck shop voucher. All right, now, okay, so we need to remember certain patterns that, again, you would have seen before in year 10. Just going to demonstrate those patterns. All right. One was called the difference of 2 squares. And that was a pattern that looks like this. If you had A plus B, A take B. So the same expressions, except one's plus and one's minus. Now I'm going to show you how you get the rule. I'm going to expand that manually using the claw. Quickly though. So it equals A squared take AB plus AB take B squared. Now those two terms in the middle cancel each other out. If I add 4 and take 4, they cancel each other out. If I add x and take x, they cancel each other out. So those two go, and you're left with this, A squared take B squared. And that's essentially the difference of perfect squares. It's that A plus B, A take away B, expands to A squared take B squared. Now, what does that mean in practice? Well, you can do certain expansions really quickly. So, for example, if I had x take away, or x plus 5, x take away 5, I can instantly go, oh, it's going to be this first component squared, take away the second component squared.
Can I have just a few minutes because it's really disgusting? Or you
I have to keep going.
Okay.
It's all right.
Okay, no worries.
Okay, so there we go. So the important thing is, yeah, it's the first value squared take away the second value squared. Only happens in this pattern. That part has to be the same as that part. We have to do the same thing at the start. We've got to just have the same thing as the second expression as well. Plus, minus. All right, that's quite cool. And it's quite cool factorising going the other way. But believe it or not, that's not what we're doing today. Today we're just mastering the expansion. We will review going the other way in due course. So look, I could write that as x squared take 25. All right, so the second one I've got to go through is perfect squares. So a plus, so that was a difference of perfect squares, and difference of 2 squares, and this is perfect squares. Often this is presented as 2 rules. I really prefer to present it as 1, but essentially it looks like this. If you have a plus b squared, that's the same as writing a plus b, because it's everything inside the brackets squared. So it's a plus b times a plus b. If I use the claw on that, need another colour. I end up with a squared plus ab plus another ab plus b squared. those two there can be combined, leaving us with a squared plus 2ab plus b squared. That is a rule known as perfect squares. Now, you could also do this with subtraction. If you had a take away b squared. To cut a long story short, do the same process, you'll end up with a squared plus subtract 2ab plus b squared. So the only thing different there is the subtraction results in a take away 2ab. Now that allows a lot of bits and pieces to be expanded relatively quickly. So for example, if I had 2x take away 3 squared, this is in effect the a component, this is the b. I go, well, it's going to be a squared, which is 4x squared. Remember to square the whole lot. So it'd be a squared, take away 2 times a times b, which is 2 times 2x, which is 4x, times negative 3, which is negative 12x. We've actually got 2 negatives there, so it'll be plus 12x, and then plus b squared. b is negative 3. It'll end up being plus 9. And that doesn't seem completely right, does it? 2. Oh, yeah, that has to be subtract. Because in this rule, it assumes already that in the middle there is subtraction. So b is regarded as just being 3. So when I did 2 times a times b, it would have left me with 12x, and it assumes that the subtraction continues through. It has to end up with a subtraction in the end. That's why I got myself stuck there, because without the subtraction, I mean, if you expanded that out normally, you'd definitely get 2 elements of negative 6x, so there had to be a negative in the answer. Anyway, there you go. That's what happens when you do mathematics too early in the morning. It's just not natural. All right, so be careful with that. If you're assuming it's negative there, then it's got to be negative at the end. Now, what else do we have to do there? You've got plenty of opportunities to practice that, and we've essentially done examples quite similar to what the text ends up doing anyway, not the same ones, thankfully. So that leads us on to the third thing I want to review today, which is something called rationalising the denominator. Rationalising the denominator is essentially the idea that we don't leave square roots in the denominator of fractions. So, for example, if you ended up with an answer that looked like this, 2 over root 3, right? We want to remove the square root. Now, what we do to do that is we multiply it by 1. Because if you multiply anything by 1, you'll know that, well, it doesn't change the value. So, if you think about, if I said, what's 3 divided by 3? You'd probably say 1. What if I said the square root of 3 over the square root of 3? It's still the same number divided by itself. That's equal to 1. Any number divided by itself is 1. The way we get rid of a square root on the bottom, therefore, is we multiply by 1, where we use the same square root value as the denominator. And if you remember your fraction multiplication, you multiply along the top, you multiply along the bottom. So on the top here, I get 2 root 3, and on the bottom, the square root of 3 times the square root of 3 gives me 3. And you'll find that if you put those values in your calculator, this initial fraction and this new one, put it in your calculator and work out the decimal value, you'll work out that they're exactly the same. So we're not changing the value of the fraction. We're not changing it at all in terms of the numerical value. All we're doing is getting rid of the square root from the denominator. Now, you can get more complicated ones than that. I'll give you a general rule for what we're doing. If you have some value over the square root of b, to rationalise that denominator, you're always going to multiply by that denominator on the top and bottom, which will leave us with a root b on top. And you tell me, what am I going to get on the bottom when I do the square root of b times the square root of b? No matter what b is, square root of b times the square root of b is b. That's essentially the whole process of rationalising the denominator on a general basis. But I'll probably do a couple of weirder examples. What could we do? Another couple of examples. Let's say I had 3 over the square root of a. So to get rid of the square root of a, I'd multiply it by 1 in the form of the square root of a times the square root of a. Along the top, I'll have 3 square root of a. On the bottom, square root of a times square root of a will leave me with just a. I hope that's cool. And what about something odd? 3 root 2 over 2 root 3. That looks like fun. Again, the square root, the surd, often you would have been taught this as surds. Essentially where square roots are involved, they're called surds. Anyway, to get rid of the root 3 on the bottom, again, we'd multiply everything by root 3 on the top and the bottom. So that would give us, remember, if you've got a square root times another square root, you can actually multiply them together. You'd end up with 3 square root of 6 over square root of 3 times square root of 3 will be just 3. So you end up with 2 times 3 on the bottom, which is 6. We can simplify that fraction. 3 over 6. So I'll be left with, well, 3 over 6 is 1/2. So I'm left with the square root of 6 over 2. That's really a 1 there, but we don't need to write a 1. Okay, so that's all pretty cool. Now, wow, we're pretty well towards the end of this. So last thing to note is for practice in this area, I'd like you to have a go at, so your practice using our standard text is exercise 2C1. And we'll go for core, I've got do all of them. And extension, I've got questions 3, 4, and 5. All right, are we generally happy with that? Looks all right, doesn't it? Might do a quick check. Grab one of my calculators out. See, I wonder what happens if I put in the square root of 6. Whoops. So if I go square root of 6 divided by 2, what does it do? Oh yeah. Doesn't want to simplify that anymore either. Sometimes the calculators are a bit of fun to see what they like to do with these things. Ha! Hey, look at that. This one actually does the rationalising the denominator automatically. See the bottom question there? I put that in the calculator and it gave me our simplified solution. That's pretty cool. Anyway, hope you enjoyed that. Have a wonderful day. Don't do anything I wouldn't do. See yous.